Okay, this is problem number 31 from the book that we got started in class, but there was a small error, so I'm here to correct that. If you recall, this is our function, a nice trig function. We take the derivative very carefully. Derivative of cosine is minus sine. I've got to use the chain rule here. I bring the 2 out in front, don't change the cosine, but then I take the derivative of that. Watch those negative signs carefully, that's what messed us up in class. But you'll see I've written it here, minus 2 sine theta, minus, and then 2 sine cosine theta. I factored out the negative 2 sine theta. What's left behind is 1 plus cosine theta. Okay, so then to set this first derivative equal to 0, I get a solution. I get a 0 only when theta is equal to 0 or 2 pi. Remember, the domain is theta is equal to or greater than 0 and less than or equal to 2 pi, so I've got to try both of those. And then I also get a 0 here at theta equals pi. Okay, so then taking the second derivative after finding the zeros and the potential local max, local min type thing, the second derivative, I'm just going back up to this factored form. I think that's easier than going up here and doing a product rule. In this factored form, I can just take out the negative 2. The derivative of, in this case, it's going to be, this is our a part times the derivative of b. The derivative of that is 0. The derivative of cosine is minus sine. So like I said, I've taken out the minus 2, and then the derivative of cosine is minus sine plus, and then this is the b times the derivative of a, which is the derivative of sine, is cosine. And so now I just need to clean this up. I've got minus sine squared of theta, and then cosine squared of theta when I distribute this back in. Okay? Well, I've got that trig identity that sine squared plus cosine squared equals 1, so I can replace the sine squared, but not the minus sign, with 1 minus cosine squared. I distribute in the minus sign, and I get plus cosine squared, and I've got the plus cosine squared, so nothing cancels out. And if you are careful with the minus sign being brought into the 1 and then put things in order, I do get a quadratic form for that, and I can factor it. I think the signs maybe are different from class, but I've still got that minus 2 out there. That doesn't change the fact that it's going to be 0 when this factor equals 0 and this factor equals 0. So again, when does the cosine of theta equal 1/2? So I get a 0. That's going to happen in this case at, that would be what, cosine is 1/2 at pi over 3, and then also at 5 pi over 3. Okay, and here it's going to be 0 at pi. But that's already one of my zeros up here, so that is not an inflection point. Okay? Remember, to be an inflection point, it has to be positive or negative when I plug it in. So I can go to graph it now, and to graph that, I'll draw my axes here, and I'm going from 0 to pi to 2 pi. And when I plug in 0, just to go back to our original, when I plug in 0 I get 1, 2 times 1 is 2, and I get 1, 2 plus 1 is 3. When I plug in 2 pi I get 3 for the same reason. When I plug in pi I get negative 1 times 2 is negative 2, and then I get negative 1 squared, which is positive 1. So negative 2 plus positive 1 gives me negative 1. So looking at my graph here then, I will go up 1, 2, 3. I start right there at 0, 3, and I finish right here at 2 pi, 3. And at pi, I'm down here at negative 1. Now that's an unfortunate place. I'll put the pi right there, and there's my point. I'm at pi, negative 1. Okay? So it's up here, it's going down, it's going back up. The inflection points are at pi over 3. Okay, well let's see. When I plug in pi over 3, Okay, I had a little technical difficulty there. Yes, so we found that the zeros for the second derivative are pi over 3 and 5 pi over 3. So those are inflection points. So if I plug those into the original function, that is just a typo there. I plug that into the original function, I'll get 1/2. I'll get 1/2 times 2 is 1, and then plus, well, 1/2 squared is 1/4. So 1 plus 1/4 is 1 1/4. So I'm here at 1/3 of the way to pi is about there, and I go up to about there. That's our inflection point. Okay. If I plug 0 in to our second derivative, I plug in 0 and I get 1. 2 times 1 is 2 minus 1. That's a positive. And here it's a positive, but there's the negative 2, so that's negative. So it's concave down, and then it's going to be, let's find the other point here at 5 pi over 2, that's, or pi over 3, there's pi over 3, and this is 5 pi over 3, and I plug that into 5 pi over 3, this pen is not being very precise, but that's 5 pi over 3, plug that in, and for the exact same reason of pi over 3, I get 1 1/4 or 5/4. Okay, so I'm here and I go up 1 1/4 and I'm right there, and for the same reason that 0 is a local max and it's concave down, this is concave down, and if I plug in pi into our second, whoops, I plug in a point. I can't use pi, but I can plug in a point on either side of it, and I will get a concave up. I will get a positive, and so it's concave up. All right. So that's the basic shape. That's pi over 3, and then 5 pi over 4. That's 5 pi over 3, and also 5/4. So I'll sneak that in like that. All right.